Looks like it's 11:05, so I guess we'll start right now. So welcome everyone to our Data 1001 Revision Workshop, hosted by UNSW Data Science Society. So our agenda for today, or could we get everyone to please sign the attendance form first? I'll give everyone 30 seconds. And what we're going to be covering today is we're going to be doing a little welcoming. Then we go cover over the three cornerstones, being statistics, computer science, business, and then we'll have time for Q&A afterwards. So could you please sign in using the attendance form? All right. The attendance form is in the chat if you guys missed it. So welcome to UNSW DataSoc. So what we are is that we are founded in 2017 with now over 4,000 plus followers. We are the largest data science society in Australia. We're an open community platform to connect and educate and empower all students. And we discover how data shapes our world and host career, educational events, and social events. You can check out more using our UNSW DataSoc Facebook page. I'll hand it off to Meet to start with statistics.
Hello everyone. So we'll start with statistics. Let me share my screen. Okay. So we quickly jump into set operations. We all know the basic part of set operations that it contains two sets, mainly A and B. And this particular thing is called the Venn diagram. So this set is called A union B. This set is called A complement. This one is called A intersection B intersection C because we have the common part of all the three sets, which you can see here. This particular set is called A intersection B because that's the common part of both the sets. This one is the disjoint set because it is not connected. And this one is A minus B because we only want the A part. Okay, that was easy. So let's look at some of the properties of sets. First of all, you have the negation property. Probability of A complement is equal to 1 minus probability of A. So complement is nothing but minus of the probability. Second thing is intersection, which is defined as probability of A intersection B is equal to probability of A into probability of B given A. We read this as probability of B given A. Then there is union formula, which is defined as probability of A plus probability of B minus probability of A intersection B. Then we have the independence and mutually exclusive properties. So these are the fundamental properties, but the important one is defined by a joint probability or multiplicative law, which is defined as probability of A intersection B is equal to probability of A given B into probability of B. So in order to for this formula to be correct to hold, this probability of A and B should be independent events. Okay. Then we have the marginal probability and conditional probability. So we are going to focus on this conditional probability today because it is quite something important in probability, because this is related to the Bayes theorem formula, and we'll look over this Bayes theorem formula with some examples. So let's quickly jump onto examples. Let's start with a very basic question. Suppose that today there is 90% chance of snow, 20% chance of strong winds, and 15% chance of both snow and strong winds. So what is the probability of snow or strong winds? So let's try to solve the question. First of all, what is my event? Let's define my event. Let A be the event, that probability of snow. B be the event, probability of strong winds. So what is probability of A? We know that there's 90% chance of snow. So the probability would be 0.90. Probability of B, it is 0.20. And probability of A intersection B, because we know we have the and, so whenever we have and, we should interpret it as intersection. So probability of A intersection B is 0.15, and we need to find out probability of A union B, because we have the or. So what formula will we use? We will use this formula, probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Just fit in the values, so it should be easy. And this comes out to be 0.95. All right. Do you guys have any doubt up until now? All good? Okay. So we'll move on. This question is of multiplicative law, or the joint probability question. Let's read the question and let's know what we have. So to gain entry to a selective high school, students must pass three tests. 20% fail the first test and are excluded. Of the 80% who passed the first, 30% fail the second and are excluded. Of those who passed the second, 60% passed the third. This may sound confusing, but let's simplify it. First of all, let's define our events. So before starting any probability question, it's always important to define the events. So what would be my events? I know I have three tests. So I'll define my event as A1, passing first test, A2 as passing second test, and A3 passing third test. So let's start. What proportion of students pass the first two tests? Okay. So we need to figure out what proportion of students pass the first two tests. So let's start with probability of A1 intersection A2. So we need to figure out this. And for this, we will use the formula of intersection. Probability of A intersection B is equal to probability of A into probability of B given A. Probability of A2 given A1 into probability of A1. So what's probability of A2 given A1? How do we read this? What is the probability of passing second test given the student has already passed the first test? So what's the probability? We know the probability of A1 passing the first test is 0.80 because 20% failed the first test and are excluded. So those who pass come under, like, so yeah. So you have 80%, you have 20%. So probability of passing the first test is A1, and this probability comes out to be 70%. Why? Because 30% failed the second and are excluded. So we know 30% excluded. So rest of them 70% pass the test. So we have 70% here, which is equal to 0.56. So that was easy. So what proportion of students gain entry to selective high school? So to gain entry to selective high school, we know that they need to pass all the three tests. So for this, we'll still use the same multiplicative law. So how do we read this? Probability of passing the third test, given that the student has passed the first two tests, into probability of passing the second test, given that the student has passed the first test, into probability of passing the first test. Okay. Uh, figuring out the probability may look complicated, but we know what is the probability of A1, that's 0.8. Probability of A2 into A1 is 0.7. We just need to figure out the probability of passing the third test given that student has passed the first two tests. So of those who pass the second, 60% pass the third. So we know the probability of passing the third test given the student has passed the first two tests is 0.60, which comes out to be 0.336. Okay. Last question. What proportion passed the first two tests but failed the third? So we'll still use this particular formula, but we'll use negation or a complement for the third test. Why have we used complement here? Because our event is defined as passing the third test. So failing the test would be like the complement of it. Okay, that's good. We'll still use the same formula into probability of A2 given A1 into probability of A1. We know this formula 0.8, this is 0.7, and this is uh of this 1 minus 0.60, that's 0.40 into 0.7 into 0.8. That's 0.224. Okay. Now let's move on to a bit difficult question. In this question, a diagnostic test for a certain disease is claimed to be 90% accurate because if a person has the disease, the test will show a positive result with probability 0.9, while if a person does not have the disease, the test will show a negative result with probability 0.9. Only 1% of the population has the disease. Okay. If a person is chosen at random from a population and tests positive for the disease, what is the probability that the person does in fact have the disease? This may sound complicated, But let's simplify and start with defining our events. So whenever you want to define events, read the question and try to figure out what probability do you know. In this question, we know that only 1% has the disease. So my first event would be that the person has the disease. Okay. And my second event would be if a person has the disease, the test will show a positive result with probability 0.9. So we know the probability of the test showing the positive result. So let's say the person tests positive. Okay. So let's give this B and A. So probability of B given A. What is the probability that the person tests positive given the person has the disease? If a person has the disease, the test will show a positive result with 0.9, while if the person does not have the disease, the test will show a negative result. That's the complement. So it's still 0.9. And only 1%. Remember, it's only 1%. So it would be 0.01, not 0.1. Be careful about this 1% because I've made mistakes in the past. I don't want anyone else to do the same mistake. So, what probability do we need to figure out? We need to figure out what is the probability that the person does in fact have the disease. So, if a person is chosen at random from the population and test positive for the disease, what is the probability that the person does in fact have the disease? So, we need to figure out probability of A intersection B. The probability of a person who has the disease given that the test is positive. Okay. So we'll use this base theorem formula. We need to figure out this, and we know this, and we know this as well. Let's see how do we know this. So probability of A given B is defined as probability of A intersection B upon probability of B. So this can be also written as probability of B given A into probability of A upon probability of B. So we know this, but we don't know this. Okay. So looking back at the formula, you can see this particular thing is expanded as this. So we can write as probability of B given A into probability of A upon probability of B intersection A plus probability of A intersection A complement. This is same as the formula, so there's nothing new in this. But we still don't know what is the intersection of A or intersection of A complement. So we'll further break down this using this particular set of operation. That's probability of P given A into probability of A upon probability of P given A into probability of A plus probability of P given A complement into probability of A. Now what information do we don't know? So we have the probability of B given A, that's 0.9 into probability of A 0.01 upon 0.9 into 0.01 plus. So yeah, we don't know this information. We know this. So we don't know what is the probability of B given A complement, but instead we know what is the probability of B complement given A complement. So how do we figure out this? So probability of B given A complement is nothing but 1 minus probability of A given A complement. 1 minus 0.90. Okay. 0.1 into, this is A complement, so that's 1 minus 0.01, so 0.99. Fitting in the values, we would get the answer of 1 by 12. Okay. Uh, I'll give you a suggestion to practice this type of question, because in exams there is a very high probability that questions from Bayes theorem would be asked. We'll quickly go over this question, and I'll try to explain this question using some different method. We'll use Venn diagram to solve the questions. So employment data at a large company revealed that 72% are married, 44% are university graduates, and half of the university graduates are married. So let's say probability of M is 0.72, probability of G is 0.44, and probability of M given G is 0.50. Probability of the person being married given that he is a university graduate, because we know that half of the university graduates are married. First question, is neither married nor university graduate. Is neither married nor university graduate. Make sure to get acclimatized with the complement thing. So this particular set operation can be given as, so this is my Venn diagram. I have M, I have G. M complement intersection G complement. Okay. So what is this? It's all the space which is given here. Okay. So that's 1 minus probability of M union G. You can figure out the M union G using the union formula, and after doing the calculation it turns out to be 0.06. Okay. Second, do you guys have any doubt with this Venn diagram? All good. The second part is married but not a university graduate. Is married but not a university graduate. So how will the Venn diagram look for this? That's M, that's G. So M intersection G complement. So we know G complement is all this, and this is also in fact the M intersection G complement. So this, how will you write this? So it could be given as probability of M minus probability of M intersection G. Okay. So probability of M is the whole, and minus the probability of M intersection G would give me this red area. So after solving this, you should get 0.5. You know the probability of M, you know the probability of M intersection G. This can be calculated as probability of M given G into probability of G. You have this, you have this. Okay, last. Is married or a university graduate. That's pretty easy. Is married or a university graduate. That's pretty straightforward. Just fit in the formula, or you can always do 1 minus probability of M intersection G, and this will yield you like, you know, this answer. So 1 minus 0.06. Yeah. So you see, there are different ways to solve the probability question. Using Venn diagrams make it very easy, and it's very easy to understand. Do you guys have any doubt? No? So I'll pass on to Alex to further explain random variables and different distributions. Thank you.
Thanks, mate. Now I'll go over the types of variables. In data science, you'll be presented with different kinds of data. They can be qualitative and quantitative. Quantitatives are numerical, like integers, and qualitatives are categorical, like animals. On the qualitative sides, they can be ordered, called ordinal, or not ordered, called nominal. An example of this could be like animals versus grade. And in quantitative side, you can have countable, discrete data and continuous measurable data. An example of this would be height versus age, or age being the discrete variable and then height being the continuous measurable variable. Now we'll move on to random variables. So while some variables can be defined, in some cases you won't know what the variable is set to, hence it's called a random variable. They can either be discrete or continuous, and the main difference is if you want to find a certain value in a discrete variable, you take the summation of that, and if you're dealing with continuous variable, you do the integral. As you can see, if you want to find the probability of an outcome, it will be normally a sum, whereas if you take a probability of a range for a continuous variable, it will be more likely be an integral, as you can see with the expected values and the summation of probabilities for the discrete variables. And now we'll move on to our distribution. The first one being the Bernoulli's trials. The definition of Bernoulli trials is an experiment with two possible outcomes. The outcomes are often labeled success or failure. An example of this would be heads versus tails, where the Bernoulli trials have a parameter of 50%. So with a Bernoulli trial, they have one parameter, which is the probability of success, and the probability of success is between 0 and 1. It is also modeled with the probability function given here, which is f of x equals p to the x times the complement of p, which is the probability of success, to the power of 1 minus x, which basically tells us the probability of a success when x equals 1, which is p, and then the probability of failure, which is x equals 0, which is the complement of that. And then the mean for Bernoulli's trial is P, and then the variance can be calculated using P times the complement of P, which is 1 minus P. And this is very useful when going into binomial distribution. So what binomial distribution is a discrete probability distribution that describes the number of success in a fixed number of independent Bernoulli trials, each with the same probability. So an example of this would be if you were to flip a fair coin 10 times, and the number of heads, which is counted as successes in this case, follows a binomial distribution with n being the number of trials equaling 10, and the probability of landing a head being 50%, which we consider success here. There's 3 conditions that must be met for a binomial distribution. The first one being there's only 2 possible outcomes. Each trial must be a success or failure, and the trials must be independent from each other, so they can't influence one another. So if you flip a tails one time, that result will not affect future results. And then probabilities and trials are constant. So every time you flip a coin, that coin has the same probability of getting a head or tails, and the trial numbers are fixed. And then if we look at the right, this is the parameters required for a binomial distribution. So the probability of success must be between 0 and 1. And to calculate such successes, or like the probability of getting that much success, we can use the formula, the probability function formula, which states that we choose n, which is the number of trials, choose the number of success we want, which is k, times the probability to the power of number of success, which is, and then times the complement of that times the probability of failure. And this works for all k values from 0 all the way up to n, which is the number of trials. The mean can be calculated using the number of trials times the probability of success, and the variance can be calculated using the number of trials times the probability of success times the complement of that. And we'll use that for our next slide, where we go over a binomial distribution example. A very simple one would be like a factory produces light bulb, and the probability that a light bulb is affected is 0.05. And in this case, we'll say our success is 0.05. If the quality control inspector randomly selects 20 light bulbs from the production line, what's the probability that exactly 2 of them are defective? So we know that we can distribute this example as a binomial distribution, where n being 20, as there is exactly 20 light bulbs being selected, and the probability of success, probability that a light bulb is effective, is 0.05, which is 5%. So we want to find the probability that exactly 2 of them are defective. So we want to find the probability that x equals 2. And if we remember, if we go back to our formula, we can use this probability function formula, which states that if we do 20 choose 2, which is the number of trials times the number of success, times the probability of success to the power of the number of success, which is 2, times the complement of failure, times the complement of success, which is a failure, to the power of the number of failures, which in our case will be 18, which is calculated by taking the number of trials minus the number of successes, which is 2. And this would result in the probability of exactly 2 of them being defective as 18.9%, rounded to 3 significant figures. Do you have any questions on that? All right, I'll just move on. We'll just do questions at the end. The next distribution that we have is a Python distribution. So a Python distribution is a discrete probability distribution that expresses the probability of a given number of events occurring within a fixed interval of time or space. And a great example of this could be the number of cars passing through a toll booth in a certain period of time, given that the car passes independently and the average rate is known. The last part is important for a Python distribution, and because of the conditions. And the conditions for it to meet a Python distribution is that the event must occur independently. So no 2 cars are like coordinating with each other. The average rate is constant. So ideally, in a world where the number of cars passing a toll booth is stays a constant, the same rate across the whole day, is the best for a Python distribution. Well, in reality, this is not the case, but we can assume it's the average rate is constant. And then the two events cannot occur at the same instant. So it cannot be going through a toll booth and not going through a toll booth at the same time. And the Python distribution is limited when the number of trial n is indefinitely large. This is important for when you're converting between, let's say, a binomial distribution to a Python distribution. Now we go over the variables of Python. We can say that a distribution is distributed by a Python distribution using this notation, where lambda is the average rate of the event occurring, and the expected value of x would be lambda, and the variance would also be lambda. So moving on to our Python distribution example, let's say a customer service center receives an average call of 10 calls per hour. What's the probability that a center will receive at least 2 calls in a given hour? So we can say that we can model the distribution using x being Python distributed by lambda equaling 10, as we can see here, of an average call of 10 per hour. We want to find the probability that the call center or the customer center will receive at least 2 calls. So probability that x is greater or equal to 2. And since Pythons can definitely go forever, we can just take the complement of that, which means it will be 1 minus the probability that x is less than 2. And the probability that x is less than 2 is basically the probability that x equals 1 and probability x equals 0, you can see here. And we can plug this in, x equals 1, into the Python distribution formula, which states that the probability that x equals a certain value is the lambda to the power of x times e to the negative lambda over x factorial, where x is 0, 1, 2, 3, up to infinity. Where lambda is the mean number of occurrence in the interval, as we stated before, and e is the Euler's constant. So if we go back to our example, we can find the probability that x equals 0 by substituting x as 0. So it'll be 10 to the power of 0, e to the negative 10, which is our lambda, to the 0 factorial, which equals e to the negative 10. And then we can do the same for x equals 1. And then if we go to the probability that x is less than 2, we can just do e to negative 10 plus 10 to the e to negative 10, which we just add them together, and that'll be 11 to e to negative 10, which then the probability that x is greater than or equal to 2 would be 1 minus that. Now we'll go on to our last distribution. This one will be the normal distribution. So a normal distribution is a continuous probability distribution characterized by its bell-shaped curve. It is defined by its mean mu and the standard deviation sigma. An example of a normal distribution would be like the height of the adult human, where most people are close to an average height, and then there's a few very extreme tall or short people. The conditions for a normal distribution means that it must be symmetrical and it must be unimodal, which means there's only one peak, and must have a bell-shaped curve, which looks like this. Yeah. And be symmetrical around the peak. So the normal distribution can be calculated using this formula, which can be simplified to a standard normal distribution, which we will use here, which is x to the minus mean over standard deviation, where mu is mean and sigma is standard deviation. The expected value of x for normal distribution is mu, and the variance is sigma squared. Cool. Now we'll move on to a normal distribution example. An example of this would be the weight of adult male lions. So the weight of adult male lions in a particular regions are normally distributed with a mean of 420 pounds and a standard deviation of 40 pounds. We want to find the probability that a randomly selected lion weighs between 380 and 460 pounds. So first things first, we want to show what distribution we're using and what parameters. So let's say X is normally distributed with mean 420 and variance 40 squared, which we can calculate by taking standard deviation squared and the mean here. And what we're trying to find is the probability that X is less than 460 but greater than 380. And if we go back to our formula before here, we can convert this into a standard normal distribution where we take X minus the mean over standard deviation, and then we can find the corresponding value here for the 460. And then this will be the probability that Z is between one standard deviation from the mean. That's basically what it's saying. As you can see here, and this is the value you'll find in your normal distribution table. So the probability of one standard deviation away from the mean would be, if you look here, it's quite hard to see, but if you search up the standard deviation table, the normal distribution table, you can find a value 1, which will correspond to this value. And then vice versa, you find the value -1, which will correspond to this value. In a normal distribution table, it will only go up to 0. And so to find a negative value, it will just be the complement of the positive value, which means it will just be 1 minus whatever 1 is for -1. And then if we can take the difference between this to find the percentage or the probability that a line lies between one standard deviation, which is going to be 0.6826%. 0.6826, which is equal to 68.26%. The next question we have is, what weight corresponds to the 95th percentile of the lion's weight? To find this, we want to find the X value that contains 95 percentile, and we can use that by using the mean plus the Z value at 0.95. So we want to find the value on this table which corresponds to 0.95%, and then we can times that by the sigma or the standard deviation. And we know that the mean here is 420, and the probability the Z value for 95% is 1.645, and then we know the standard deviation is 40, so we can times those two together and add it onto 420, which will equal 485.8 pounds, which is the weight corresponding to 95% of the lion's weight. Now we'll move on to the central limit theorem. So the definition in the textbook is basically says, suppose x1, x2, all the way to xn is a collection of independent and identically distributed random variables where the expected value of xi is mu and the variance is sigma squared, which is less than infinity. Then as n approaches infinity, the distribution of random variable square root n, the mean of x, minus mu converges to a normal distribution with mean 0 and variance sigma squared. And basically what this means is regardless of the original distribution of the population, the distribution of the sample mean will approach a normal distribution as the sample size becomes large. It basically describes the behavior of the sum of average of large numbers of independent, identically distributed random variables, which will always tend to a normal distribution. And this assumes that is independent and identical distributed variables. It has a finite mean and variance. And the application of this is you can use it to estimate confidence intervals or approximation if you don't know the distribution of the original sample. Yeah, and I'll head it off to Sam to talk about computer science.
Yep. Thank you, Alex. And let me share my screen so we can start off with the computer science part. Yep. So I hope this is visible. So in the computer science part, we'll be looking at a lot of topics, which include binary search tree, decision trees, graphs, big data, and Bloom filter. So let's begin. So first of all, binary search tree. So a very easy definition of a binary search tree is that this tree always has a maximum of two children, right? And also there is a golden rule you should always remember. So a binary search tree needs to maintain a specific order, which is that the left subtree should always have lesser values than the original node values, and the right subtree should always have greater values. So a good trick to remember that is less on the left and more on the right, right? So if you observe this example tree over here, if the root node is 8, to the left, all the values are lesser than 8, and to the right, all the values are greater than 8, right? And let's have a look at some definitions that we need to know. So the root from which we start is called the root node. The value is called the key. The line connecting is called the edge. The nodes at the end, right? If there are no nodes after that, they are the last nodes. They're called leaf nodes. If you take out a particular section of a binary search tree, that's a subtree. And this would be an example of a parent node, and these two are its child nodes. And we could say that these two are, both of these are siblings to each other. So 3 and 16 are siblings, 22 and 40 are siblings, and so on. So now let's look at the three traversal methods for traveling across a binary search tree. So they are in order, pre-order, and post-order. And the simplest way to remember how they work is the rule of traversal. So for in order, the rule goes left, root, right. For pre-order, the rule goes root, left, right. And for post-order, the rule goes left, right, and root. So let's take this example and try to derive the in order, pre-order, and post-order traversal for this binary search tree. So let's start with the in order traversal, right? The rule says left, root, and right. So let's begin from the root node A. The rule says left. Okay, can we go left? Yes, we can. So we move to the left. We are at B. The rule says left. Yes, we can go to the left. So we've arrived at D. Can we go to the left here? No, we can't. And the root, well, this is the root and there's nothing to the right of it. That is why the first element will be D. Now, after the left comes the root. So we go to its root, right? And we print out that. That's the next one. And then comes the right value, which is E. So we get DBE following the rule of left, root, right. Now, we had originally started from the root A, right? And we've covered everything to its left. So we come to the root, which is A. So the next element is A. Then we go to the right. And the right section has another subtree in it, right? So we come to C. We apply the rule left, root, right. Is there something to the left? Yes, that's F. So we print out F, then the root C, and then finally G to the right. So that's how you get your in-order traversal. Now for pre-order, the rule says root left, right, right? So pre-order is pretty easy. You always take the root first. So A, okay, A. Now root left. To the left is B. When you come here, again root, so root gets printed B. Then root left. Okay, you go to the left, root, okay, root gets printed, that's D. So root has been printed, there's nothing to the left, nothing to the right. You go back, root has been printed, nothing to the left, something to the right, that's E. So the next one's E. Now you go back here, root has been printed, the left has been printed, the right's left. So again, you go here, you go root, left, right. So that's how you get C, F, and G. And for post order, the rule is left, right, root. So post order is a little trickier compared to the others. So we go left, right, root, right? So we start from here. Okay, left. Yes, we can go left. Left. Yes, we can go left. Can we go left? No. So D is the first one. Now left, right, root. So to the right is its sibling E. So that's printed first, and then comes the root B. We go back to A, so we've printed the left, we have not printed the right. So we go to the right first. Out here, we go to the left again. So we go to F, so F gets printed, then right, then G, so G gets printed, and then root C. And now that we've done the whole left subtree, the whole right subtree, we finally go back to the root node, which is A. So that's how you get the, um, oops, yeah, the in order, pre-order, and post-order. So any questions? No? Okay, I will move on. So as you saw, these properties of the binary search tree are very useful for us for these three operations, which are searching, insertion, and deletion. These three operations are what we'll be looking at today. So let's start off with searching. Let's say you have this given binary search tree and you want to search for the element 3. So searching is very simple. All you need to do is look at the root node, right? Then you see if the value you need to search for, is it lower or greater than the root node? 3 is lesser than 4. So it has to be on the left side. So you only look at the left subtree from now on. You go to 2. Is 2 lesser than or greater than 3? 2 is actually lesser than, which means it can't be to the left, it has to be to the right. So you go to the right and you've found your answer. So searching is pretty simple. Now, if you talk about inserting, inserting is also very similar to searching, where you just need to follow the rule, right? So let's say you want to insert 8 in this subtree. So you'll start at the root node 4. You'll see that 8 is greater than 4. So we have to insert the value to the right subtree. So we go to the right. We see 6 here, which is still lesser than 8. So we can't have it to the left of 6. So we still go to the right. We see 7 here, and that's still lower than 8. So we can't insert to the left of 7. So we insert it to the right of 8 since 7 was a leaf node now. So we've inserted it here and our binary tree's logic still holds. Now, deletion is a little more complex because it has three kinds of cases, whether the binary search tree has no child, has one child, or has two children, right? So let's start off with a basic case where if we have a leaf node, right? So if we want to remove this node 18 from the binary search tree, we can do it directly. We can just remove it and our binary search tree is still valid. None of the rules are broken, right? So if it is a leaf node, you can simply delete the node and you don't need to think about anything else. Now, if the node has one child, then it's still pretty simple. You just replace the node with its child. So let's say for this binary search tree, if you want to delete 25, all you need to do is delete that and bring 30 up instead of it, right? So your new binary search tree is still valid. The third case is where we need to be a little more careful, which is when the node has two children, right? So what you need to do is delete the node and then you replace with the in order successor or predecessor, depending on the kind of tree, right? So let's see this example where you've got this binary search tree, the 15 is the root node, and we want to delete this node out here, number 20, from the graph, right? So we'll see that uh, since we want to delete number 20, let's just look at the basic logic we've learned, right? We've learned that what's at the root, it has to be lesser than the right value and greater than the left value. So we can't really put 18 over here if we delete this because um, there's 19 left over here, right? Which is greater and it's still part of the left subtree. We can't put 16 because again, 18 and 19 remain. So the in order predecessor in this case would be the value 19. So we lift 19 up, replace it and delete off 20. So if you see the binary search tree here, the left subtree has remained unchanged and the right one, it's got a 19 over here. So 19 is greater than 15, that's valid. 30 is greater than 19, that's valid. And both 18 and 16 are lesser than 19. So this is still a valid binary search tree and you've deleted a node with two children. So now let's move on to some questions. Do you think that this is a valid binary search tree? Can I have some responses in the chat? Or yeah, I'll just wait for a few seconds. No, no. Yeah, I see a few no's. Yep. So that's right. This is not actually a valid binary search tree because the node A has 3 children. And a binary search tree's number one rule is at most a node can only have 2 child nodes. So how about this one? Is this a valid binary search tree? No. No, yeah, I see a few more no's. Yep. So this is also not a valid binary search tree because the number 4 appears here in the right subtree of 5 and it's actually lesser than 5, right? Which is not possible. Okay. Is this a valid binary search tree? So you have a single node. Yes, yeah, I see a couple of yeses. So that is right. As long as a binary search tree has at most 2 children, right? It's valid. And in this case, it has no children, but it's still a valid binary search tree. So is this a valid binary search tree? No, I see. No, yeah, okay. So you're right. No, it's not a binary search tree. This is actually a null pointer, right? So for a binary search tree to be valid, there needs to be at least one node and it has to have the qualities we discussed preserved. So, okay, now let's move on to a more complex question. What if we want to remove the uppermost parent node in this binary search tree? So can you tell me what element from these will be replacing number 7? I'll give you a few seconds. Being on the right node, 9 becomes the root. Close, close, not quite. Yeah, 8 becomes the root, that's right. So we see here we want to delete the 7. So for that, we will bring over number 8 because as we see, we want the right subtree to always be greater than the root node, right? So if we have the 9 become the root node, then 8 can't be part of the right subtree. So which is why we'll be taking the 8. How do we tell whether we bring up the 8 or 3? So that's because the logic of a binary search tree, right? These values are lesser than the root node. So there's no way to replace them and still have the logic of the binary search tree preserved because, yeah, then you'll be removing the left subtree, like reducing it. So yeah, that's a rule where you always go to the right subtree when you want to delete a node and replace it. So yeah. Now, yeah, let's move on to decision trees. So a decision tree is a, a sort of a data structure where we deal with decisions instead of storing information, right? So we use a combination of mathematics and statistics to conclude what variables are more important to reach a decision, right? So something could be, an example could be, let's say the weather. If the weather is sunny, cloudy, or rainy, right? Now, if it's sunny, is there high humidity or is it normal? Or is it windy? Is the wind strong or is it weak? So that's how we keep making this decision tree and we arrive at an answer, right? So the structure of a decision tree looks like this. It's sort of similar to a binary search tree where the topmost node, right, is the root node. Then uh, if a node has children, that means it's a decision node. And any other nodes which are at the end, they are all called the leaf nodes, which are they have no children, right? So some important terms that matter to us in decision trees is entropy and information gain, right? So we look at entropy first. Entropy is a measure of uncertainty in the target variable y. So how we calculate entropy is with this formula. And what we do here is we take the log base 2 of the probability of I or the event y happening, right? We multiply it with the probability of the event y happening. So log to the base 2 probability of the event multiplied by a probability of the event. we add a negative sign, and then we add a summation, which means that we'll be adding together all the values for which we want to find the entropy, right? The next concept is information gain. Information gain is a measure which is used to quantify the reduction in entropy to help data partitioning, which means it's a measure to reduce the uncertainty, and that helps us build a decision tree, right? So let's look at an example. Let's say that you want to buy a new smartphone, right? And you're looking at just two features, which is smooth performance, let's call that feature X1, and long lasting battery, let's call that feature X2, right? So you have four options. The names of the phones and the models, all of those don't matter, right? What we're looking at is just these two features. So we put in a 1 if you want to buy the phone, and we put in a 0 if you don't want to buy a phone, right? So the first question here would be, what if we want to find the entropy of y, right? So to find the entropy of y, the entropy is denoted by h, right? So h of y, we apply the formula, which is summation minus, so this is just a negative symbol, right? The probability multiplied by the probability log to the base 2, right? So if you see the table over here, we can find the probability of y equal to 0 and y equal to 1. We'll see that we have four values, and two of them are 1, which would be 2 by 4, and two of them are 0, so that would also be 2 by 4, which is half. So the probability of y being equal to 0 and 1 is half each. So now we just plug in these values in this formula. So we'll have minus half, which is probability of y 0, multiplied by log to the base 2 of 1 by 2, minus again half log to the base 2 1 by 2, which comes out to be 1. And that means the uncertainty is very high, right? Because higher the value of entropy, the more uncertain it is. The lower it is, the more certain you are. So now what if, for the same example, we want to find the information gain of x1 and x2, right? So how much information can we gain from the feature x1 and the feature x2? So to do that, let's say we denote the information gain of x1 with gain of x1, right? So the formula would be the entropy minus the conditional entropy given x1. So gain of x1 would be entropy of the event happening y minus entropy of the event y happening given that the feature x1 is present, right? So now if we calculate it, the entropy of y given x1 would be, sorry, probability of y given x, right, would be probability of x equal to 1 into entropy of y given x1 is 1 plus probability of x0 into entropy of y given x1 is 0, right? So first we'll calculate the entropy of y given x1 is 1, which would be same formula, right? We see that the probability of, so when is y 1? Y is 1 in just two cases. When is x1 1? It's 1 in three cases. So probability of y given x1 is 1 is 2 by 3. Similarly, it's 0 only in one case, right? And x1 is 1 in three cases, so that's 1 by 3. And you can also find out probability of y given x1 0 will be 0. Probability of y given x1 is 0 will be 1. So we just plug in the values, minus 2 by 3, log to the base 2, 2 by 3, and minus 1 by 3 log to the base 2 1 by 3 comes out to be 0.918. And when we calculate it for conditional probability of y given x1 0, plug in the values again, we get the value of 0. So now that we've gotten these, we put that in our formula for finding the entropy of y given x, right? So we say probability of x equal to 1 into conditional entropy here plus probability of x0 into conditional entropy here. Plug in the values and we get 0.6885, which would be around 68.8%. So to finally find the gain, we say the entropy of y minus the entropy of y given x1, right? Which would be 1 minus 0.6885, which is about 31%. So this means that the feature x1 is giving us 31.1% of the information we need to find out if we want to buy the smartphone or not, right? So I'll give you a minute if you want to try out uh, finding the information gain of x2 in the exact same way how we did it for x1. So yeah, I'll wait for about a minute if you want to solve it. Otherwise, I'll move on and show you. Okay, so just for the sake of time, I'll move on and I'll show you the final calculations. You'll find that the conditional entropy of y given x2 1 will be 1. Conditional entropy of y given x2 0 will also be 1, right? So the gain actually comes out to be 0, which means that in this case, smooth performance as a node is what we'll be basing our decision on because its information gain at 31% is higher, right? So how the decision tree will look like is if the phone has a smooth performance, if it's yes, then yes, I'm going to buy the phone. Otherwise, I'm not going to buy the phone. Now, obviously, this decision tree is not perfect, right? And it's not going to work in all cases. But with the amount of data that we had, which was just 4 cases, this is what we can construct, right? So now we'll move on to the next topic, which is Bloom filters. So what's a Bloom filter? This is a space-efficient data structure which is used to quickly check if an element exists in a set or definitely not exists in a set. So what I mean by that is a Bloom filter will always tell you if an element is absent in the set, but it can probably tell you if the element is present or not in a set, right? So let's look at an example. Let's say that you want to create a new playlist of songs, right? So we use a mathematical function called the hash function. It doesn't really matter to us how the hash function is working. Just know that it's sort of assigning a unique value to your variable. So let's say we want to add the song Love Story, right? Our hash function assigns it a value of 48, okay? And we want to add a few more songs. We add Hotel California, Jailhouse Rock, and Dancing Queen. So our hash function computes the values 32, 12, and 29, right? So what will happen is that our Bloom filter, it will activate the bit values of of the values that the hash function calculated. So that's 12, 29, 32, and 48, right? So 12, 29, 32, 48. What the Bloom filter does now is it has flipped this bit to 1. So all these bits are initially 0, right? Each of these cells is a bit. It's turned these particular values to a 1, indicating that this exists, right? This is our set, and these values exist. So now, let's say you want to stream a song called Here Comes the Sun, and you pass it through your hash function, and it gives you the value 7. Now, you want to use your Bloom filter to find out if the song Here Comes the Sun is already present or not. So you ask your Bloom filter. The Bloom filter checks all its values, right? It sees that the bit 7, it's still set to 0. It's not been initialized. So it'll tell you that, oh, you do not have Here Comes the Sun in your set, which means that that's correct, right? We don't have it. We only have 4 songs, and Here Comes the Sun is not one of them. So it correctly identified it wasn't present. But the thing to be careful in a Bloom filter is that there may be false positives. So let's take a case. Let's say you have the song Purple Rain, and your hash function gives you the value 29, right? Now you may remember seeing the value 29 previously, right? And well, that can happen because if your hash function is quite simple, it may end up generating the same value even if the input you gave it was different, right? So now when you ask it if purple rain is in your Bloom filter, it'll check 29, the bit is flipped to 1. So yes, it'll say it's there, but it's actually not there, right? So it's giving you a false positive, saying that something is present when it's not. So to solve this problem, what we can do is have either a more complex hash function or several different hash functions. So let's say we have many hash functions, right? And we put the song Hotel California through them. It gives us these three values, 4, 48, and 11. So we'll initialize the bits for all of these to 1, right? And now if we have a new song, right? And we use a hash function to get 4 values, which is 5, 49, and 11. Now you see, 11 was also there for the previous song. So there's still a chance of messing up. But when we actually go and check, we'll see that 11 is initialized. Its bit is 1, but the rest of them, which is 5 and 49, they are not initialized. So in this case, it'll correctly tell you that Billie Jean does not exist in your song playlist, right? So this is how we can solve the problem by having multiple hash functions. So unless all of them pass, unless all of them are flipped to 1, it'll conclude that no, you don't have it, right? So let's go for some questions. Which of the following is an impossible property for a Bloom filter retrieval, right? So retrieving an element that is indexed in the array and in the set, indexed in the array but not in the set, not indexed in the array and in the set, and not indexed in the array and not in the set. So if anyone wants to share the answer, they can quickly put the option in the chat. Okay, so the answer in this case is option C, which is not indexed in the set and in the set, right? So we can't retrieve an element which was never indexed in the array and it's not even in the set. Yeah. Okay, what about this? What's the impact of adding too many elements to a Bloom filter or setting the false positive rate as too low? So your options are, it will reduce the memory consumption, it will improve the accuracy, it will decrease the computational overhead, or it can lead to an increased chance of false positives. Wait for a few seconds. Okay, so the answer in this case is option D. If you, so the statement reduces the memory consumption is not true because adding too many elements actually increases the memory consumption, right? And saying that you improve the accuracy of the Bloom filter is also not true because if the number of elements increases, the false positive rate may also increase, right? It will actually reduce the accuracy. And saying that it decreases the computational overhead of adding elements is also not true because that may increase if the filter needs to be made bigger to have more elements, right? So what's definitely true is having too many elements can increase the chance of false positives, right? Because if your hash function gives you the same values as we discussed earlier. So, okay, another, I think, last question for Bloom filters. Which of these following statements are true? Give you a few seconds. Okay, so the answer is actually all of these are false. It was a trick question. So the statement allows for efficient element removal. It's not true because deleting elements means you need to have more complex techniques. Precisely determining false negatives. Well, the thing is, false negatives can never exist because as we defined in the first slide, a Bloom filter guarantees the absence of elements. It can tell you probably if an element is present or not, but if it's about the absence, it will always guarantee that an element is absent. So there are never any false negatives in a Bloom filter. Does it have a built-in mechanism to avoid false positives? That's not true. We can try to reduce false positives, but we cannot eliminate them entirely, right? And does it guarantee 100% accuracy in element containment? That's also not true, right? Because we'll have false positives and that'll make us not have 100% accuracy. So yeah, that was Bloom filter. Let's move on to big data now. So the most important thing for big data is knowing your three V's, right? Which are volume, variety, and velocity. So volume means the scale of the data, right? Which could be measured in terabytes, petabytes, right? All of that. Variety would mean the different types of data, which could be relational data such as SQL tables, it could be text data, It could be semi-structured data such as XML, CSV files. It could be graph data, or it could even be streaming data, right? And velocity refers to the speed of the data transmission. And this is usually real-time data, right? Such as in healthcare monitoring, stock data monitoring, and video streaming. So we'll have a closer look at streaming data, right? Because streaming data is all around us, whether when we do data analysis in our IoT apps, such as if you have a Google Home or an Alexa, right? If you want to do financial analysis or get real-time recommendations. So there's characteristics of a data stream that you should remember, which is that a data stream is continuously flowing and has infinite data volume. It is chronologically significant, which means the time at which certain elements enter and leave matters. It's unique and could possibly be non-homogeneous. There could be different types of data. And it's also very noisy, rapidly changing, and the input rate needs to match the output rate. Now, two useful approaches to handle streaming data are sampling and sketching. Sampling means you're taking a fixed proportion of the data, right? For example, you're using a sliding window approach where you take the most recent 100 data samples, or you're doing something like taking one value out of 10. So if you see this example, we have all these dots, these four colored dots, and we just take a small sample of them to denote that, okay, red had the most volume, yellow had the least. And another method is sketching, which means retaining a small statistical summary of the data where we use approximation algorithms and concentration inequalities. So most of this is just theoretical based. You just need to know these facts, right? So sketching would be something like when you draw a sketch of, let's say, a criminal or something. You don't need to have the exact picture. You can just draw a rough sketch if you've never seen the person before, and that can help you find them. Now, what is Hadoop? Hadoop is an open source distributed computing framework, and it's designed specifically for analyzing big data, right? And the three properties of Hadoop are that it's got redundant fault tolerant data storage, it allows you to use a parallel computation framework, and it allows you to use job coordination. Now, Hadoop uses a strategy called MapReduce. And what's MapReduce? MapReduce is a big data programming model, right? It was developed by Google in 2004. And it's basically got two main functions, which is mapping and reducing. So, mapping means that the data is split into smaller independent pieces and then processed parallelly, right? And reducing means that the data is shuffled, then combined efficiently to give you a concise output. So if you see this example, this is a classic example of a word count process. Let's say you have this huge bunch of words, right? Now, what it'll do first is it'll split it into three categories, right? It'll randomly split it. So there's deer, bear, river over here. Then it'll map each of those, right? So there's one value for each of those. It'll shuffle all of those together, right? To combine similar ones and then finally reduce them. So there's two bears, three cars, two deers, two rivers. And finally combine it back to give you your final result. So MapReduce is really efficient and completely changed the scope of big data when it came out. Now let's move on to graphs, which is another big topic. So, a graph is a non-linear data structure that is used to represent relationships between objects through a network of nodes and edges. So, you can use various terms. You can use vertices, edges, whatnot, and it's denoted as G, V, comma E. So, the graph, vertex, comma edge. And two most simple types of graphs are undirected and directed. Undirected is when the edges have no direction, right? Such as an example would be Facebook, where if someone sends you a friend request, you both become friends. And directed means the edges have a certain direction, which would be something like Instagram, where you both need to follow each other uh, to be following each other, right? There's also weighted and unweighted graphs, where the weight is sort of the cost to travel from one graph to another, but we'll not concern ourselves with that right now. So, how do we represent graphs? There's two methods, that is the adjacency matrix, right? So a 2 cross 2 matrix where each row and column is one of the elements, right? So 0, 1, 2, 3, 0, 1, 2, 3. Now, how we fill in this matrix is if a node is connected to another node, we put in a 1, otherwise a 0, right? So if you see the 0th row, that's for this element 0. It's connected to 1, 2, and 3. So 1, 2, and 3 get a 1 filled in. Since 0 does not have a self loop, it gets a 0. For 1, it's connected to 0 and 2. So for 0 and 2, we get a 1. Other places, that's 0. That's how you fill out this adjacency matrix. And an advantage for this is that edge lookup is extremely fast. But since we need to fill in this matrix, we need to reserve space for every possible link, even the ones that don't matter, such as the zeros. And the second way to represent graphs is via an adjacency list, right? So here's when we represent the graph as an array of linked lists, right? So it's a very similar concept where, let's say 0 is connected to 1, 2, 3. So the linked list will have 1, 2, and 3 in it. 1 will have 0 and 2 in it. 3 is connected to only 0. 2 is connected to 0 and 1. So this is more efficient in terms of storage because we only need to store values for the edges which are connected. There's no like, if 1 is not connected to 3, 3 does not need to be present in the linked list, right? Now, what are graph operations? We can do a lot of operations on a graph, which could be check if an element exists. We can do graph traversal. We can add elements to the graph, or we can find the path from one point to another. So we'll be looking at graph traversal, right? And two important data structures for graph traversal are stack and queue. So a good visualization would be stack could be like a stack of pancakes where you stack them on top of each other, and a queue such as a queue of people, right? So we'll quickly look at these two data structures. The queue, right? So this works on the first in, first out principle. So if you just remember this, that will help you recall how it's used, which means that whatever element goes in first comes out first, right? So when you're walking in a queue, if you're first in line, you're going to get your stuff first and then move out of the queue, right? And the operations we can use are enqueuing, which means insert, and dequeuing, which means removing. There's also is empty, is full, and peak, but we'll only concern ourselves with these two for now. Similarly, for a stack, stack works on the first in, last out principle, right? Which means that the last element inserted will be removed first. So think about if you've heard of the towers of Hanoi or the pancake stack, we saw that, right? If you stack pancakes on top of each other, you'll eat the one on top first, and you'll continue eating all of those until you reach the very bottom one. So even though the bottom one was cooked first, you're gonna eat it at the end, right? And for stack, the insertion operation is known as push, removal is known as pop. So now let's look at our first algorithm, which is the breadth first search or BFS. So the BFS is a vertex-based algorithm, so it consumes more memory. The idea behind it is that you explore all the nodes at a given depth before moving on to the next level. It uses the queue data structure as we just saw, right? First in, first out. The structure of the path would always be wide and short. It's optimal for finding a shortest path to a node, and it's always guaranteed to return a solution, right? So if you look at this example binary search tree, how you would traverse using the breadth first search would be start off at 0, go to 1, then 2, then 3, 4, 5, 6, right? So you're always going level by level, exploring all the nodes. So 0, explore everything, 1 and 2. Okay, 1, explore everything, 3 and 4. 2, explore everything, 5 and 6. That's how BFS works. So let's solve a question for BFS to make it clear how this works. I will move to a whiteboard to show you that. Give me 1 second. Okay, so sure. Okay. So I hope you can see this whiteboard now. So this is the example breadth first search that we want to solve. So given this graph, we want to find what happens when we start from A, perform a breadth first search starting from A, right? So the data structure we have to use here is going to be a queue, right? And we'll also maintain a list of what we visit. Remember, this isn't exactly a queue. This is just a list of the order of visitation. So we start at A, right? So we've added A to the visited list. Now, breadth first search means exploring all the possible nodes for a given node. So from A, where can you go? You can go to B, you can go to D, and you can go to E. So that's exactly what we do. From A, we go to B, D, and E. So we add B, D, and E to our queue, and we add BDE to the visited list as well, right? Now, what after that? For each of B, D, and E, we are going to visit all the possible nodes, right? So let's say for B, we can visit F, right? For D, we can visit C and H, and for E, we can only visit H. So you can go in any order you like, right? Let's say I start at D. I say that I can visit uh oh, sorry. Yeah. So we already had BDE, right? So since we are exploring B first, we remove it from the queue, right? And we have F. So I wanna visit F first. So I add F to my queue, right? Then once I have said that, okay, from B, I cannot go to any other place, like because the direction matters here. I can only go to F. I've added F. So let's remove B now. So B is gone, right? And we move on to D. So for D, I can visit C and H. So we add C and H. We remove D now. Now there's only E left, and from E, you can visit H, which is already there. So you can remove E as well. You have FCH left, and your visited order is A, B, D, E, F, C, and H. Now, finally, as you saw from here, we had FCH, right? Now, from the node F, we can visit I and G, right? So we can add G and I, and that actually completes our traversal. So our visited path becomes A, B, D, E, F, C, H, G, and I. So, a breadth first search doesn't usually have a single answer. You can do it any way you want. Like if this graph didn't have directions, right? You can do it in whatever order you want and it will work as long as you're going level by level, right? So now let's move on to depth first search. So depth first search is an edge-based algorithm. So it consumes lesser memory, right? The aim of depth first search is to explore as far as possible along one direction and then explore other possibilities. It uses the stack data structure, right, which is first in, last out approach. The structure of the path is narrow and long, and it's optimal for solving puzzles with a single solution. But it can get stuck in an infinite loop because, let's say, in an imaginary situation, if you have a tree, right, or some sort of game logic where you can keep going deeper and deeper into a level, you'll actually keep going deeper without exploring the rest of the game. So that's why if you use DFS in a situation where there are multiple solutions, you can sometimes get stuck. And let's also solve another DFS question, right? The same graph via DFS. So let's move on to the DFS. So for DFS, we'll be using a stack, right? So again, we start off at A. Now, A is at the bottom of the stack and we want to pop it off now. So we put it in the visited. After A, we can visit either of B, D, or E, right? So we add E, D, B. We can add that in any order. Let's say I decided to add that in E, D, and B. So B is at the top of the stack, right? So we're going to pop off B first. We add that to our visited list. Now from B, we can go to F, right? So we add F to the top of the stack. And now from F, we have the possibilities of going to G and I, right? So we pop off F from the stack as well and add in G and I. So our visited list has become A, B, F, and G, right? Now, let's say I want to pop off G because I want to visit C. So I pop off G, add in C at the top of the stack. And now from C, can I visit anything else? I can visit B, but B is something I've already visited. So I'll pop off C now. I'll explore I now. I'll go to I, right? Now I is at the top of my stack. Can I explore something from I? Yes, I can explore H. So I pop off I go to H instead, right? And I've added I to my visited list. Now from H, can I visit anything else? I cannot. So I pop off H as well, right? Now what do I have left? I have D and E left from my original starting point. So I'll go back to D. Can I visit anything from D? No, actually I cannot visit anything new. So I'll pop off D as well. I'll go to E. Is there anything left to explore? Nope. So pop off E as well. Your stack's finally empty. And you've got your depth first search traversal. So that's A, B, F, G, C, I, H, D, and E. So I hope that made sense. Let me stop sharing and okay. So the final thing we have, the final concept is the K-core algorithm, right? So the K-core algorithm is pretty simple. It means that every node in a subgraph should connect to at least K other nodes, right? Or it should have at least K neighbors or have a degree of K, okay? So a degree would mean the number of edges that a node has. Let's say the degree of this node A would be 1, 2, 3, right? It's got 3 edges. The degree of C would be 1, 2, 3, 4, 5, 6. Degree of G would be 1, 2, 3, 4, 5, right? And if you take this small subgraph, this could count as a two-core graph because you see E is connected to G and F is connected to E and G is connected to E and F. Now, what's the maximal K-core algorithm? So this is when you want to find a particular K-core graph, right? You recursively keep deleting all the nodes that have a degree less than K from the graph. So the step-by-step procedure is whenever you get a graph, just label the degree of each vertex, right? Start from the smallest degree and remove the node and the edge if it's less than K, update all the remaining nodes, and then keep repeating this process. So let's solve this question over here and find the maximal 3 core, right? I'll quickly share my whiteboard again. Right. So we want to solve this problem right here, okay? And what we're going to do is label each of the vertices. So we see V6 is called 1, 2, 3, 4, 5. V5 has got 1, 2. V4 has 1, 2, 3, right? So this way, as you can see, I've already labeled all the edges to save time. Now you'll see that only V5 and V12 have 1 and 2 edges, right? And what we want to find is 3 core. So anything that's less than 3 connections, we remove. So we'll remove that. You can see I've deleted them and the graph remains. Now we'll relabel the graph again, right? So we relabel them. We find out, okay, 4, 6, 4. V8 has only 2, right? V4 has only 2. So again, the ones which have less than 3, we're going to remove. Then we get our new graph after removing them. We add them back. We again relabel them, see that, okay, these two are only 2 again, remove them, right? Our graph has become smaller. Now we again relabel all the vertices, see that, okay, this one still has 2, remove that. And finally, we've obtained this maximal K 3 core graph, which where every node has at least 3 or more connections, right? So that was an example. Think after this, yeah, that was the end of all our computer science part. So let's take a 2-minute break and also take a picture. So yeah, if you are good with turning on your camera, please do. Otherwise, no pressure, because we do need a picture for housekeeping purposes. Gallery. Yeah, so give me 1 second. I'm gonna take a picture. So okay, 3, yeah, everyone ready? 3, 2. Okay, I'm ready. Yeah. I thank you so much. So we'll take a quick 2-minute break right now and move on to the final business part.
Hello everyone. I hope my voice is clear because I have a little bit of flu, but let's start into the business part. Okay, so in the business part, we're going to discuss about the ML versus econometrics, data collection, data structures, sampling and selection bias, and also linear regression. Okay, so we're starting on the types of data collection. So the first part, we have primary versus secondary data collection. Primary data collection is data collected directly from a source, usually raw data. For example, like the attendance sheet you submitted before is our primary data collection. And then there's also a secondary data collection, which is data collected by an individual who is not the original user. For example, data we get from the ABS website. It's because we are not the one who collects the data, it's called secondary. It's just taking in other people's data. Next, we have qualitative versus quantitative type. I'm sure you guys are already familiar with this data collection, and then I will just touch on and I'll read it again for you guys. Qualitative data collection is data that does not need to be subject to a crucial mathematical deduction, which is just not a number. Like for example, what degree do you study? What is your favorite colors? Those data cannot be converted into numbers, which is why it's called qualitative. And then quantitative data is data represented in numbers and do require mathematical calculations to deduce. For example, distance from home to UNSW or your mom. And then why do we need effective data collection methods? First of all, it's for integrative research. Second of all, it's to reduce likelihood of error. And third of all, it allows for identification of target consumers, which can reduce the cost. And then we also have types of data structures. We have 3 types of data structures. I'm going to discuss the cross-sectional data models first. Cross-sectional data model measures the same variable at the same point in time across different individuals. Like for example, right now, let's see the temperature in your suburb right now. And then time series data models, it will measure the same variable across the same individual, across different point in time. Like for example, we measure different temperature in your suburb, like for example, let's say Randwick, across different years from 2020, 2021 until 2024. And then there's also spatial panel data models, which measures both. So it measures the same variable across different points in time and across different individuals. Like for example, each of you, one lives in Randwick, one lives in Mascot, one lives in, I don't know, let's say North Sydney. You guys fill out the temperature in your suburb from 2020 to 2024. And we can say this data model is balanced if all individuals are in all same time periods, and then it will be unbalanced if one of the data is missing. So I hope that's clear. We're going to move on to the next one. Next, how do we collect the data? So we have two methods of data collection. The first one is observational, and the next one is experimental data. Observational data observe relationship between explanatory and response variables, where the researcher is not in control of response variable. So it's just we don't manipulate anything. Like for example, it's we can say how many cars are passing through UNSW Anzac Parade that is red. So how many red cars are passing through Anzac Parade in for say 5 hours. But however, this one has a problem because it's ineffective at determining causal relationships and then very long research time required. Next, we have experimental data, which we can assign a treatment to a group and observe changes in response variable. It is generally stronger evidence than observational data and much shorter research time, although it is more expensive. One of the famous experimental data collection is, for example, the effect of amount of water on plant growth. Then we can say put 5 plants and then we'll give each different water throughout say a week. For example, this one gets no water, this one gets 10 milliliter of water, this one gets 20 milliliter, and so on. And then we can observe the plant growth. Let's say how much they grow in a week, and then there you have it. That's our data. And then next we also have natural experiment case study, which is kind of unique because it's called experiment, but we observe it. So the researchers take advantage of naturally occurring events or changes to study their effects rather than manipulating conditions themselves. So us as a researcher, we cannot manipulate them, but we can take advantage of what is already being manipulated. So for example, we can see the impact of smoking ban on heart attack rates. Let's say there is a smoking ban in Randwick local government area for 6 weeks. And then during the 6 weeks, we can see there is a 40% decrease in heart attack rate. However, it goes up again once the ban is lifted. Here, us as a researcher, we can observe and compare the changes in heart attack rates before, during, and after. However, we cannot choose which suburb we want the ban to be. Like, we cannot say, I want it to be in Parramatta instead. No, we can only observe the effect on Randwick because that's what being imposed by the government. Next, of course, on data collection, we have to get samples. Why? Because it is inefficient to perform experiments and analyze the entire population of data. So it would take samples to represent the population because it's really tedious to ask everyone, for example, say in UNSW about their WAM. You can just take a sample. Like for example, let's take 10 people from engineering. Let's take 10 people from CS. And then there you have it. That's our sample. However, there might be selection bias where the sample does not represent the general population. I'll read out what selection bias is first. Selection bias is an error that can occur due to a non-random sample of the population, when some members of the population are less likely to be included in the sample than others. This will cause your sample to be biased. Like, for example, a survey about job satisfaction is conducted only among employees who frequently attend company events, potentially excluding those who are less engaged and must be less satisfied. For example, like in that example, we are only asking the ones who frequently attend, and then we don't ask the ones who don't attend, which means the one not attending itself might be like, I'm not interested in the event, I'm not engaged, I'm not satisfied with that. And then we cannot see the effect. We cannot take the data from them because we're not asking them. It makes no sense. And then one of the examples of selection bias comes from samples are self-selected. Self-selected samples bias occurs when individuals are given the freedom to decide whether or not to participate in a particular study. The bias can occur as individuals who choose to participate might differ significantly from those who do not. Like, for example, we conduct an all-out survey asking people about their preferred diet. However, it's a self-selected sample, so samples are voluntarily, I will fill out these online surveys, but we cannot ask everyone to fill out, because only they fill it out. And then if we're asking about their preferred diet, maybe the ones who care about their diet fill out more, maybe those who are more healthy fill out more, and so we cannot get the general population data. And then when we are doing some experiments and taking data collections, there are some things to consider. The first one, is there any confounding variable, and has it been controlled for? Confounding variables are external factors, like for example, in our plant growth experiment where we put some water on and watch the plant growth. Maybe we confounding variables is the sunlight, maybe it's humidity, and then how do we control them? Like for example, if it's humidity, they are kept in the same room, or if it's sunlight, they are given the same exposure of sunlight. And then the second one is, how do your variables of dependent and independent interact with each other? Does it make sense? Like for example, we'll do an event of listening to Taylor Swift songs on plant growth. It doesn't make sense. It doesn't interact well with each other. And then here's an example question about Jenny Craig. This is pretty famous in our Data1001 course. I think you guys have seen it before, but I'm going to read it again. So Jenny Craig is a weight loss intervention, and then their commercials show a photo of some celebrity before and after joining Jenny Craig. So this is the before, and this is the after, which seems to work in this case. And then we have a question. So what are the control and treatment in this experiment? And then are you worried about any selection problems and why? And then so for the control of the experiment here is the weight before the treatment, and the treatment is whether or not they are joining Jenny Craig. So the control is maybe we can standardize them, or like the starting point is 75 kilograms for all participants, and then that's our control. And for treatment is just whether or not they are joining Jenny Craig, and then we can compare the samples who joined Jenny Craig before and after, and then those who do not. Let's say, for example, in 3 months. And then for B, Jenny Craig are likely to choose only success stories because they are the one who do the marketing, and so and then data collection, they can just choose the people who are more likely to be successful because it will be beneficial for them, their branding and their marketing. For example, they can choose healthier people who exercise a lot, because they're more likely to lose some weight compared to those who do not. Next, we will also have some linear regression. So it's been touched on the statistics segment, but now we can also iterate again. So we can think linear regression is as the formula here, where y1 equals b0 plus b1 times x1 plus e1, where y1 is the dependent variable, b0 is the population y-intercept, b1 is the population slope coefficient, x1 is the independent variable, and then e1 is the random error term. And then for multiple linear regressions, say we have multiple variables, we can use this formula where similarly b1 is the population slope coefficient, and then x1 is the variable 1, and x2 is the variable 2, x3 is the variable 3. So y1 equals b0 plus b1 times x1i plus b2 times x2i plus bn times xni. And then the b1 and b2 here, it represents the causal effect of x and y, which is also how y changes if y is changed ceteris paribus, or holding other variables constant. Until now, is there any questions? Okay, it seems like there is no question, so I will move on to the next one. So here is an example of our linear regression. So consider an experiment where an agency would like to see the effect of modifying a car on its market value. All stocks or unmodified cars are on control group, and then we represent them by x1 equals to 0, and then all modified cars are in treatment group, where x1 equals to 1. The agency then records the car prices, the y1, and then all else is used to estimate the parameters of simple regression. This is the formula of a linear regression. So the price is a b0 plus b1 times x1 plus u1. And then assuming all other factors are kept constant, like for example type of cars, type of modification, and then the years of cars, which of the following is not correct? A. The OLS estimate of b0 will be the sample mean of y for everyone in the control group. B. Positive estimate of b1 provides evidence supporting the hypothesis that the modifying car leads to an increase in its market value. C. The sample mean of y for everyone in the treatment group will be equal to the sum of OLS estimates of b0 and b1. And D. OLS estimates of b1 will be the sample mean of y for everyone in the treatment group. I will give you some time to think about this, and if you feel like it, you can put your answers in the chat. Thank you, Lisa, for answering. Your answer is correct. I will discuss on why is that so. Okay, so in option A, The control group has unmodified cars, xi equals 0. So for the control group, b1 equals b0 times b1 times 0 equals to b0, which is why it's only b0 here. So the intercept of the regression model is a sample mean of y. That's why option A is true. And for the option B, the regression parameter represents the causal effect of x and y. And then here, if b1 is positive, then increase in b1 with increase in x1 will also increase in y1. As you can see here, if this one increase, this one will also increase because this one is a positive. Or the estimate will increase since we are adding positive value, which is what I just said. And then since y represents the market value, b1 being positive does support the hypothesis that the modification has led to an increase in the value. That's why option B is true. And option C, treatment group has modification, which means x1 is going to be equals to 1. And for the control group, it's going to be y1 equals b0 plus b1. The sample mean of y is sum of all estimates of b0 and b1. That's why option C is true. Because this one equals to 1, that's why it's b0 plus b1. And option D, it contradicts option C, which is why it's false. And so the answer here is D. Next, we have confidence intervals, which measures the uncertainty in sample variable, which will differ depending on the sample size. It just means how sure we are that our answer is like correct. And so this is the formula of our confidence intervals, where the standard error of the mean equals to S over square root of n, where S is the sample standard deviation and n is the number of observations in the sample. Here we have larger sample sizes, we have narrower CI because it's divided, which provides more precise estimates. So here we favor the experiments and the data which have larger sample size because it can provide us with the most precise estimates and more valid data. For example, a 95% confidence interval will, over many repeated samples, contain the true population mean 95% of the time. And so this interval is described as mean plus and minus 1.96 times standard error of the mean. And then 1.96 is the standard deviations above and below the mean, while 95% of the observation lie. 1.96 is a z-score. So let's say, for example, you have the mean of 5 and then standard error of like 1. So 95% of the time, your data will fall in like, say, 5 plus 1.96 and 5 minus 1.96. And then another thing to note is if 0 is included in the confidence interval of a coefficient, it suggests that the variable may not be significantly impact the dependent variable. It just means that our variable may not really be impactful. And then that is it. If there is any question before we move on to the next part. If there is no question, I will pass on Meet on the machine learning versus econometrics. Meet, the time is yours.
Business part. So we'll quickly go over to last few slides. First of all, what's the basic difference between machine learning and econometrics? Econometrics is basically used for estimation, and machine learning is for prediction. Machine learning has various algorithms and it learns iteratively through data to give you the prediction. But in econometrics, we have estimation. For example, we want to estimate the effect of a salary on a university graduate. So how does the salary differentiate when you graduate from UNSW or let's say Macquarie or let's say UCID? So in machine learning, there are algorithms like clustering and classification. But in econometrics, you have algorithms like DID, regression discontinuity, and many more examples. The main part is ML stresses accurate prediction of Y, whereas econometric stresses inferences about relationship. But both of these are very heavily used in data analysis and both have their different applications. So let's look at one practice question. In a study investigating the factors contributing to business success, the research team decides to analyze currently active businesses. Okay. Sarah argues that there may exist a certain amount of bias by conducting the investigation. Do you agree? Okay, the answer is fairly easy. Yes, there is an example of biased experiment, specifically survivor bias, which is a subset of selection bias because we are only sampling from successful business and not the failed ones. Okay, thus we aren't considering the businesses that have succeeded and we cannot determine what were the useful or useless features that make a business success. So in our study, when we are looking only at the successful business, we would see only the parameters that influences a business to be successful and not the parameters that makes the business unsuccessful. So to get a whole picture, we should have unsuccessful businesses and successful businesses together in our study. Another question. Suppose at UNSW you were asked to find the relationship between weekly hours spent studying and weekly hours spent working. Okay. Does it make sense to characterize the problem as inferring whether study causes work or work causes study? Uh, to answer this question, you should really know what does this causes mean. Causes basically means that whatever we are doing in the study is affecting the work or work is affecting the study. So is it valid to say that study causes work or let's say work causes study? What do you guys think? I don't think so. It is a valid thing to say that study causes work or work causes study. I mean, there might be many different other factors that can create causal effect. For example, which university are you studying can affect what work will you get. Which degree are you studying will affect what work will you get. How much efforts are you putting into your studies? What is your grades? All these different factors affect the causal effect. So it is not valid to say that work causes study. So what is the second part? If you have found that it is not a causal study, how can we set one? So RCT is like the golden rule of causal inference. Everybody uses RCT. And the primary thing about RCT is that participants are randomly assigned to treatment and control group. That is, you have two group A and B. A has been given the treatment and B has not been given the treatment. Treatment basically means your study. So if you, for example, if you want to see how does morning lectures affect your studies, so all the students in A will have the morning lecture starting from 9 a.m. and all the students in B will do not have morning lectures. So at the end of the week 10, if you see the grades, you can make a comparison between your treatment group and control group and see how morning lectures affected your study. Then there is controlled conditions and blinding. So these two concepts are not majorly used in causal effect or causal inference, but they are still important. In blinding, both participants and researchers are blinded to group assignments to minimize bias. Participants don't know their group, and researchers and participants both don't know their group. So they are basically like just doing a study without any information. They don't know anything which group are they in. They just know the purpose and they're doing the study. One more question. Suppose there's a neighborhood called Greenvale where a new subway line is being constructed to improve transportation connectivity. The construction of the subway line is expected to be completed in 2022. We want to investigate whether the introduction of subway line has a causal effect on house prices in Greenville neighborhood. Okay. Write out equation for hedonic price model and DID estimator. So hedonic price model is nothing but an equation which is used to calculate the price of a quantity over time. Okay. So this equation is the primary equation of a linear regression, and it's also a hedonic equation where your y is the price and your x1, x2, xk are the parameters or the features. For example, number of bedroom, number of square meters, whether the house contains a backyard or not, how many on does it have a ensuite, how many bathroom does it have, how many kitchen does it have. All these features are used to calculate the price of the house. But in DID, we use something which is called as an interaction term. Now, to explain DID in few words, we basically divide the study into two parts: before and after. So in this study, we know that we need to figure out what was the effect before the 2022 and what will be the effect after 2022. Okay. So we don't know the data yet, but whenever we have data, we usually divide it in two sections, one for 2022 and zero before 2022 for both control and treatment group. So we have two binary digits, 1 and 0. This similar technique is used for the green will and control will. So control will is the control group, which is similar to green will but does not receive the new subway line. Okay, like previous example which I mentioned about the morning lectures. Control will is the control group where you don't give the treatment and you want to just see the effect of the treatment. So in this so you fit the values in this equation. This is your time variable, this is your control and treatment group, and this particular term is called the interaction term. Now you may have a question that what is the difference between the normal feature and interaction term? How is interaction term different from this? So to summarize your question, interaction term basically measures how the performance of that particular thing changes with respect to both the features and also with the price. So how will price affect given that my house is in 2022 and it is in Greenville? So it takes into account both time and the location factor. Yeah, so that was it for business section, and thank you so much for this. So we have so in this summarize this workshop, we did statistics, starting with Bayes theorem focus on this base theorem as this is very important. Set operations, probability function, diagnostic testing, types of variable. This distribution is also important. So you should also focus on this. The whole computer science is important. I mean, you cannot miss any topic from this section. You need to revise every topic, go through a recording, go through a questions. If you have any doubt, ask them. In business section, try to focus on the theory and try to answer the questions through theoretical knowledge, because there is nothing practical in it. It's just all theory, and if you know the theory well, you will be able to answer the questions. I've lost a lot of marks in business, so please try to focus more on business, as this statistics and computer science are pretty straightforward. But when it comes to business, it's not straightforward. It asks questions which are tricky to understand, but the answers are pretty easy. If you have any questions, you can ask them, or else thank you so much. I know it was a very long workshop, but thank you guys for holding on till long.
Yep. Thank you everyone for coming, and yeah, all the best for your exams. If you have any feedback for us, please let us know. And we'll send over the slides to you via email, and also try to get the recording on YouTube soon as we can. So yeah, thank you. Alrighty.